Just go.
Yes, yes, go, just go.
Hello. So I'm going to talk about GILLIAN, which is a multi-language platform for symbolic testing and verification. And I'm Philippa Gardner. And these are my co-authors. There's Jose, who used to be at Imperial and has just got an academic job in Lisbon. And there's Petter, a senior research fellow, and Sasha, a PhD student, both in my group. And I'm going to be talking about GILLIAN, which is this analysis platform for many languages. And we've only just published that work this year. Oops, excuse me. However, it's based on lots of work that we've done on JavaScript analysis, and we're now just moved to this many language platform, very much inspired by what we did previously with JavaScript. And GILLIAN is a place where we can do unified forms of compositional symbolic analysis. And what we've done is whole program symbolic testing, that's not compositional, full verification based on separation logic, and automatic compositional testing based on bi-abduction, all underpinned by a common symbolic execution tool. So for the code developer, what this means is that in the case of the whole program symbolic testing, instead of writing unit tests that you'll be very familiar with, instead we do symbolic tests, where the symbolic tests have information about how symbolic inputs and outputs given by symbolic variables behave. So in particular, we've got annotations that are first order assertions or formulae about these symbolic inputs and outputs. So this is quite specialist, but we're hoping to get this nearer to general developers at some point. And either you get bounded correctness results or you get concrete counter models saying why your test hasn't worked. Now, full verification is really meaty. And here you've got to do very, very substantial annotation to your program, and it's only there for the specialist. It's based on separation logic. You need to add pre-post conditions, invariants, lemmas, and tactics. And in particular, the real difficulty is what does it mean to be at the right place of abstraction for your program. You either get functional correctness guarantees or failing symbolic traces that are currently impossible to read except for by us, but at some point will be more easy to read. And then there's compositional testing, automatic compositional testing based on bi-abduction. And this is where the general developer has a chance to play. And the people that are doing the most on this, or the ones that were starting this, are the well-known Facebook Infer crowd. And it's based on, their work is based on a technique called bi-abduction, which we also use. And the point about this work is that it's very minimal annotation for the in the code, meaning the general programmer is not having to do very much to the code. And you end up either with bounded correctness specifications or lightweight bug specifications. And the point is, because everything's so automatic, there's only tiny lightweight bugs that can be done. And there's a real choice point to make about how much information to give back to the general developer in terms of how much is going to overload that general developer in terms of it's just too much information. But Infer got a sweet spot there. So let me talk about the GILLIAN platform. It's underpinned by general intermediate language, hence the name GIL, hence the name GILLIAN. And this is where we do the symbolic analysis. It's an intermediate go-to language this is normal. There's a lot of work in industry and in academia on such intermediate languages, and there's a choice point about what language to use. And then what we have that's novel is that it's parametric on the memory model of the target language, and I'll say more about that later. We've got a first order solver powered by the Z3 theorem prover. We're believing we're doing a good job with that, but we don't believe we're particularly novel. And then something that is novel is that our work unifies 3 types of analysis. We've got modular analysis about symbolic execution, abstraction, bi-abduction, in order to do symbolic testing, verification, and automatic compositional testing. So we've got this GILLIAN platform. And what the first thing that happens is that it needs to be instantiated to a particular target language. And in our case, we're going to focus on JavaScript and C. And this is done by a tool developer, but at the moment, the tool developers are ourselves. And eventually we want to get the work to a stage where the tool developers can be other people. And what's needed is that you need OCaml implementation of the concrete and symbolic memory models and a trusted compiler from the target language to GIL. We have a concrete memory model so that we can test how our compiler is doing. And we have a symbolic memory model in order to do our analysis. And we find that we want to keep this separate because we're doing optimizations here that are not needed down here. And we're finding it quite, some quite subtle choices going on. So we want to keep things separate. This compiler from the target language to GIL, it preserves the memory models because we're analyzing the structure of the memory models, and it preserves the semantics. And what is really going on is that if we have control flow in the target language, we're just translating it to control flow in the go-to language. So there's not much difficulty there. The difficulty is making sure that we're linking closely to whichever language standard we are working with. And we have example instantiations. We actually really like this GILLIAN while instantiation because it's a toy language, but the memory model needn't be toy. So we can actually work on abstractions of particular memory models without having to think lots about this compiler up here. We've got, we are looking at real world languages, and in particular, we're looking at GILLIAN-C and GILLIAN-JS for JavaScript. And the point about these two is that they have very different memory models. C is a block offset memory model. We use the COMSERT compiler, so it's extremely trusted because it's part of, it's in the COP theorem prover. And we found bugs in Collections-C, a real world data structure library. So there we've mainly concentrated so far on symbolic testing. Right now we're doing a lot of work on verification. But for the purpose of this talk, I'm going to say more about JavaScript, one reason being that the memory model is so simple that I can show you how GILLIAN is working. And so this will be the main topic of our, the rest of the talk, and it's working with this extensible object memory model. We very much just started GILLIAN Rust. There's other people that are further ahead than us. And we're doing it with my student, Sasha, who's also part of this work. And the reason for this is saying, no, not old C, let's do modern Rust. And one can only sympathize and love the journey. So inside GIL is this common symbolic execution engine. I'm not expecting you to read this formal stuff. I'm a theorist, I like the formal stuff. So I have a formal operational semantics for this symbolic execution engine because I only have a tiny little go-to language. I can write this down properly. Even though people tend not to, it is possible. And if you don't want to look at the formal semantics and instead like OCaml code, you can look at the OCaml code and they match very closely because that's the point of our agenda, is to understand how much of how we're thinking theoretically can be got into the actual tool development as well. And sometimes we have to go way into hacking and grunge and what does it mean to do things as fast as we can. But here we don't need to. And then the user inputs, these basic actions that are fundamental interactions between the language and its memory. So for example, most languages have some version of what's it mean to be a heap cell. It can be done in different ways. And given this heap cell, what does it mean to get and set information about this heap cell? This is what I mean by a basic action. And then we have this parameterized action rule that basically, given the actions we have, here's alpha meaning action, given the actions we have, then what does it mean to hook this to the rest of the symbolic execution engine? On top of this basic core engine, we have abstraction. Now, abstraction says you've not only just got this heap cell, this concrete heap cell or symbolic heap cell, one also has this assertion for saying in a symbolic place, what do we mean? So in particular, anyone who knows separation logic, we know there's a cell assertion that has a direct link to the underlying heap cell assertion. Excuse me, the underlying heap cell. So we have the notion of heap cell assertion and the getters and setters associated with those assertions. And what the getters and setters here mean, they're slightly different from the concrete stuff. It means you've got the memory that you're working with. We're now in partial land because we're working with separation logic. And given this partial land, what does it mean to take off the bit of the memory that's corresponding to this cell assertion? And one might have a bigger assertion made up of lots of cell assertions. So one ends up taking off all the memory that you want to do with the particular assertion that you're handling. And then what does it mean to set it back again? And one does this by working at the level of core predicate, then building up. We have additional rules that we need to add to the underlying basic symbolic execution tool. And in particular, we reuse function summaries because now we're in verification land. And we also fold and unfold user-defined predicates. And this is where a lot of the work has to be done. So you've got these core predicates then and the underlying heap cells. This is the sort of starting point. But actually, what does it mean to build up abstractions and get to the place where the code developer understands the interface? There's a huge amount of work that needs to be done there on abstractions and user-defined predicates. And then one has, we have to unfold and fold these predicates, which we do with these rules. In the tool, the folding can be automatic. The unfolding often needs, sometimes needs some nudging. So this is where we have to really understand how to get the tool to be as semi-automatic as we can. Then, as well as abstraction, on top of this core execution engine, we then have bi-abduction giving the automatic compositional testing. And one insight that we have is that with these basic actions, we have this, we operationally describe these basic actions, and in particular, we are very, very cautious about saying what the success cases and the error cases are. Quite often in operational semantics, one talks about success and doesn't give the error cases. But here we give the complete information about the success and error cases, and errors can sometimes be fixed. And that's what bi-abduction means. So one can have an error like 3 plus true, and no way can we fix that. That's a real error. but we can have an error that says we haven't got the resource we need to do the job. We haven't got a particular heap cell that we need to do the job. And we can fix it automatically using bi-abduction and add that to the precondition that we are working with. So an error can have many possible fixes, and the tool developer needs to understand this. And this can get quite subtle because actually not many people think very hard about the underlying memory model of a language. If we think about C, it's extraordinarily difficult memory model. The people that do think very hard about it actually are people that worked in the Coq theorem prover world. So whether it would be CompCert or Robert Kreber's work, they're thinking very subtly about this C memory model, but a lot of people don't. And we have a single additional rule to, given an error, sometimes you can fix it. Everything is underpinned by formalism, and so we can characterize correctness results. And in particular, our results are general, parameterized by the particular memory model that we're talking about. So if one is a tool developer and if one cares about correctness, lots of people don't, but you know, because there's more immediate things to do, not because they don't care. But if you are interested, then what you have to do is, at the level of the basic actions, you have to show the correctness of the symbolic actions with respect to the concrete actions. At the level of abstraction, you have to know that the frame is working, that your frame property is working. At the level of bi-abduction, your fixes make sense. And then we have the general correctness results. So now I'm going to talk about instantiation. So in particular, I'm going to talk about JavaScript, partly because this is where we're most mature in our results, because of all the previous work we did on JavaScript, but also because the memory model actually is very simple, even though the language is very complex. Whereas C memory model, look, there's lots of work to do. So this is why I'm on the JavaScript for now. And in particular, we've done analysis of the ECMAScript 5 strict programs. Most people who know from JavaScript know that going from ECMAScript 5 to 6 means doubling the size of the language. So this is where we're concentrating for now. We have an extensible object property memory model where it comprises the heap, domain table, and meta table. The heap is given by pairs of locations and strings, locations giving the object identifier, string giving the property, and having a partial function to values. We're a little bit subtle in the sense that we're building on the separation logic world. We're dealing with partial heaps, not whole heaps. We have the domain table that for a particular object location says whether a property is in that location. So it's giving information about what properties can be in that location. And we have metadata giving information about things like prototype chains. We also have the symbolic version of the heap memory model, which is extremely simple. It's not simple if we're in the C world. It's very different in the C world. But in the JavaScript world, the symbolic memory is very like the concrete memory, except for ones working with symbolic expressions consisting of symbolic variables and all that expression language, not just concrete locations. And we have symbolic heap domain table in metadata. And due to the partiality of what's going on, one subtlety that often gets buried in this sort of work is that we're expressing negative information. So we are partial, which means we have missing information. given that we've got missing information, but sometimes we do know. If we go to C, if something is out of bounds or something is freed, we actually know that that information really, in our hands, it's not missing. So we really need to add this to what we're doing with the heap model and the values. So inside these values, we've got negative information that's not being highlighted. At the level of JavaScript, it's saying, given a location and a property, you really know that that property is not in the object that you're working with. This is essential for compositional reason. In the JavaScript world, we've got this trustworthy compiler from ECMAScript 5 strict to GIL. I won't talk about this very much because this is part of our old Javert work. Trustworthy means it follows the standard line by line. It preserves the memory model. In our case, that's what we need. And it passes the official test suite as well as we can do. The discrepancy but here is due to behavior of OCaml strings compared with JavaScript strings. What I like about this work, it's giving a criteria for validation that's outside our system, i.e. the tests have come from the official test suite. For those of you who know about JavaScript, there's a humongous amount of complication to do with the internal functions. They're implemented in our intermediate language, the intermediate language GISL, which is what the Javert compiler goes to, and then we've gone from GISL to our general intermediate language, which is trivial. It's trivial when we've got GIL instantiated with the JavaScript memory model. JavaScript is this huge language, but it's huge due to the compiler and all the control flow. It's not huge with respect to the memory model. And we only have 8 basic actions. And I'm going to show you one of them. The others are just as simple. So here's an example basic action for JavaScript. It's getCell, and it says, given a location and a property, it's going to find the value. So yeah, it's just simple things. And in the concrete case, we've got this memory. We're applying this function to this memory. Inside the memory is the heap. The heap, if it has this location and property, then we will get back the value and we will be in a success case. Or you won't have the location and property for some reason. In this case, it's because we haven't got the location in the locations of the heap. Then we say some information, an error case about it's missing and what's been missing. There's another case to do with if you haven't got the property. And this, so we're saying we've got error and we've got the description of the error. We also have the symbolic version of that. In this case is not so difficult. In the case of C, it's much more tricky and it's different, but here it's quite similar. So here we're working with a symbolic location, which is just a symbolic expression with symbolic variables. We've got symbolic location, symbolic property, and a symbolic heap that contains this symbolic cell. So we've got to match the symbolicness of this location and property to the symbolicness of the argument that we're getting. And that's, to do that, we have this extra path condition that requires that they're equal. So what's going on with the symbolic memory is that not only do we have the symbolic heap structure, but also we have a path condition saying how the bits of information are related to each other. And what that means is in the place we're in, at the current state, we have this path condition. And now, due to this get cell, we're extending the path condition by this pi prime path condition that requires that the symbolic location of the get cell function and the symbolic location of the heap, they're not syntactically the same, but they have to be the same in the sense that they can be satisfied. Similarly with the properties. And if that's the case, we've got a success case in the assumption that we have this extra path condition pi prime. We're in a non-deterministic world because there's lots of ways that this symbolic location property pair can match the heap. It's not just necessarily by this particular cell. And we can also have the missing case as well. Now do notice something, we're working still with very, very tiny heap cells. In the case of JavaScript, we're working with this locations and properties, and we get values. We know that in JavaScript, we end up working with extensible objects. This is all got by the abstractions we're using, not the fundamental underlying basic actions. JavaScript core predicates are extremely straightforward, and people knowing about separation logic will not be surprised about this. We have a core predicate of this shape. We've got a symbolic location, a symbolic property, and a symbolic value. And we have getter and setter associated with this particular core predicate. And here I've given information here. I've just given the found cases rather than the missing cases. There's more to do here than just what I've written down. And the point is that we're framing on and off. For the separation logic people, they will know what that means. Basically, you've got the memory, you're doing the matches as before. Here's a symbolic heap, here's the match. The match has to work. And with the match, we're then framing off. So we've got the match here, and we end up with this new heap there where we've lost the match because it's the bit connected to that core predicate. So we have this idea of framing off and on, very much motivated from the separation logic work. In bi-abduction, we have the idea of fixes from errors. So I've given you this missing object error where there wasn't a location, and we got the information about the symbolic location and symbolic property. I actually walked through the case in the concrete case, not the symbolic case. But we have the same thing happening in the symbolic case. And there's two possible fixes. One fix is saying we fix by adding this new location property symbolic pair with a symbolic value. And for those of you who know about JavaScript, the values are data descriptors, and we have a symbolic variable corresponding to the value of the property. One would have different things given the different types of memory one's after, but the key point is that we're working with these fresh symbolic variables standing for possible values. But we also must have the absent case. This information is just saying not there. Given this particular symbolic location and property, we have not got the value. This is what we can do with what we have. So I'm staying with JavaScript for now. We've looked at Buckets.js. It's a standalone real-world data structure library, which is why it's really good for us. It's used a lot. And we've done symbolic testing for that. So instead of unit tests, symbolic tests. And we got an MSc student from France who was doing an internship with us. And we got him to do the symbolic tests, and he did them really well without knowing so much about GILLIAN and with GILLIAN-JS, although he did have us helping us answering questions every day. And even though the library is well used, we found bugs and they were fixed. And this is the sort of order of GILLIAN commands we're handling in this sort of time. We've also extended the work. This is actually in work that's parallel to GILLIAN in Javert, but we can easily port it over. We're doing this at the moment, which is we can extend the work with an events module and start looking at events such as DOM UI events, JavaScript promises, JavaScript async await. And in eCoop this year, we've published some work doing this events module for Javert, and looking at the cache library, which is a tiny alternative to jQuery used a lot. And in particular, we did find bugs, etc. But what we were really after was bounded correctness results. And in particular, we're able to say, if a single handler had been registered to a given event, then that is the only handler that can be triggered for that event. Sure, one would expect it to hold. It didn't. We found 2 bugs that were fixed. Now it does hold up to the bound that the length of the event type is as most 20 characters. So we're in this world of symbolic testing, we're into bounded correctness results. And the reason for that, we're not working with invariants, we're just brute forcefully unrolling loops. But the interesting point is that the unroll of the loop transfers to a property of the input that the length of the event type is as most 20 characters. So we did like that work. We've also done full verification of AWS code. I should point out this work is also with my PhD student, Gabriella. We've also done work on full verification of Amazon code, and this is absolutely all PETA. And the current way that there's some validation going on is that there's a developer inside Amazon that we've talked to a lot who does this sort of thing. Inside the code, he says the element count and the fields per element must be non-negative using this needs information. This gets checked at runtime to check that this is okay. And it is a first order formula. And we set ourselves the task of what does it mean to do full verification of this code, which trying to hook to his places where he's got some first order formulae. And we're doing the verification of this message header deserialisation procedure. This was the easiest one we could find and didn't involve things that we couldn't do, such as higher order reasoning. And it's 170 lines of code. We can specify it. I'll let you read that for yourself. It has impact on AWS code and on GILLIAN. In this particular function, we improved the code, or rather the developer did, and that's because we had the data structure which we were verifying, and his code sort of went a little bit tricksy and orthogonal to that data structure rather than properly matching the data structure. So he fixed it because he's an elegant developer, understood that the code should match the data structure. He discovered one bug, we discovered one bug and one vulnerability. We're very pleased about this. We will tell you about it. And we substantially improved the reading capabilities of GILLIAN and GILLIAN-JS. So never mind how many list algorithms we'd looked at in the past, as soon as we went to real code, we had a huge amount to do. We had that learning curve for the first time now. It took 2-person months of concentrated work, but this is PETA 2-person months, and PETA is really good. There's 2K lines of annotations for 170 lines of code. We've got a lot of work to make this simpler. Let me just, in the last few minutes, give you a little bit of a understanding of how this works. We've got the AWS message header. It's a sequence of bytes encoded as JavaScript ArrayBuffer. Here it is. The deserialisation function takes that list of bytes, converts it to a JavaScript object, and now we're working with strings, not bytes. We take this, I'm going to concentrate on this encryption context for the talk that's here. And there's 3 core functions. I'm concentrating on one associated with this encryption context. We've got this predicate. This predicate says this buff, which is this list of bytes, matches this list here, where you've got the structure of the key value pairs in a list, but still these keys and values are bytes. Either you're in the empty case or you're here. This predicate says we have a sublist of length with the length 2 bytes at the beginning. This information here is describing the numbers of key value pairs in here. First as raw bytes. This is of 2 bytes. We change the raw bytes to an actual number. That actual number is positive. This predicate here describes this structure here. This structure here consists of a field. This field here, we've got 2 bytes describing the length of the number of bytes needed to describe the key. We're in a very dynamic situation rather than static. Here we've got the values, the length and the values. And so we've got 2 field elements, KC of them. This is what this describes. We've got the first projection, second projection. We link the lengths. This is what the specification looks like. Jan, I realised the time. Should I finish dead on 3 minutes, or can I go on for a bit longer for 5 minutes?
Please continue. It's fine. We're good.
Thank you. So we've got this decode encryption context, and what it does, it takes that list of bytes and turns it into a JavaScript object with these strings. So what's happening, these are strings. This is the function that Amazon uses to turn bytes into strings. And we have here a JavaScript object given by this predicate. This predicate object says location O, there's no prototype change, and it's non-extensible. It's a frozen object, and this lot just is describing this information here now in string form. And this first order formula is saying that the information in byte form matches information in string form. The keys must be unique. The frozen return map should be frozen to prevent tampering. And now we have the specification of the function. This bit I've described, this bit I've described. This is saying we've got this bit, its first order formula is saying this is saying this bit. This is JavaScript information about the heap, more JavaScript information about the heap. What we're in the process of doing now is doing the same specification for AWS C code for exactly the same header, message header. So here we will have C heap, here we have C heap, and here we would have the same first order formulae. That's what they're aiming for. That's just the specification. The verification is huge. We have this tiny little for loop, which is only a tiny part of what's going on. We set up and established the loop invariant. We re-established the invariant. To set up and establish the loop invariant, 4 takes 27 invariant components. If you're going to have such a complicated data structure, you're going to have such a complicated invariant component. It's up to you. It's up to the code developer what they do. Re-establish the loop invariant, 9 more tactics. It's a lot of work that Petter had to do. So in order to make this work, we need no duplicate keys here, and we need to know that each key has, when we're adding a new one, that each key has not already been added, so that we want to make this unique. So we have a needs, this is the developer wrote, we need this lot being not defined. And for those of you who know about JavaScript, if it's in the prototype chair, if you can't find it here, you can go here looking for it. And this is where we found a bug. If the key coincides with the property of the object.prototype, we will end up with a bug. And we just simply cut it off and didn't have it connected to the object.prototype to get our results to go through if the code developer needs to choose what they want to do. This bug was predicted in the original theory and in the original Javert paper. It's found here, in cache, in jQuery, in recent code that Gabby was looking at inside Amazon London because she's currently doing an internship here. So this sort of bug seems to be everywhere. We were dead chuffed at this one. They'd just forgotten to freeze one of the key, one of the pathways to getting a key value object. They'd forgotten to freeze in the code. So always freeze in your code. Our verification found it. There's several caveats to our work. There's huge amounts still to do here. I will leave that for questions. And my final slide is just to conclude. GILLIAN is this multi-language platform for unified symbolic analysis, doing whole program testing, full verification, and automatic compositional testing. Of course, we have to improve all instantiations. Of course, we have to do lots of things better. Sasha's moving us to Rust to be more modern. We've done cock mechanization of WebAssembly in different works. So we've got WebAssembly in our heads. So maybe we'll move to that, we'll see. And then we've got so much more analysis to do. I was hinting at interoperability by saying that there's AWS code in JavaScript and C for the same problem. What does it mean to have similar specifications? We want to understand that much better. Of course, concurrency, given my other work. We need to look at events beyond JavaScript. And there's recent work on incorrectness logic that's having so many resonances to what we're finding in GILLIAN that we would love to port some of the ideas coming from this world to our to this GILLIAN world. And we've got a Facebook grant to do just that. Thank you very much.